Hello everyone, this video presentation is the second half of the third part of our calculus short course series, which was about the applications of calculus related topics within the scope of electrical and electronics engineering. We were reviewing some example use cases and solving some problems which are directly included in the field of electrical engineering, like circuits, amplifiers, circuit components, etc. etc. Here we will continue with our examples again. Digital logic circuits, which compress the inner workings of computers, are essentially nothing more than arrays of switches made from semiconductor components called transistors. As switches, these circuits have but two states, which are simply on and off, which represent the binary states of 1 and 0 respectively. So what can these components store or conduct as ones or zeros? The faster these switch circuits are able to change state, the faster the computers can perform arithmetic and do all the other tasks that computers do. To this end, computer engineers keep pushing the limits of transistor circuit design to achieve faster and faster switching rates. This rate for speed causes problems also for the power supply circuitry of computers, though because of the current surge, technically called transients, created in the conductors carrying power from the supply to the logic circuits. The faster these logic circuits change state, the greater the DI/dt rates of change exist in the conductors carrying current to power them. So whenever we have some sort of change within a system, it means that there is a derivative involved. So DI/dt means basically change of the current within a system, or in more precise terms, derivative of the current with respect to time. Anyway, significant voltage drops can occur along the length of these conductors due to their parasitic inductance. Also considering this information, suppose a logic gate circuit creates transient currents of 175 amps per nanoseconds when switching from the off state to the on state, or in other terms, from 0 to 1. If the total inductance of the power supply conductors is 10 picohenries and the power supply voltage is 5 volts DC, how much voltage remains at the power terminals of the logic gate during one of these surges? And for illustration purposes, we have a figure here. We have a logic gate circuit, which is given as a black box system, so we do not see the inside, but we do know that it's a logic gate, and it is driven by two inductors and one voltage supply. Let's see the solution. The voltage remaining at logic gate terminals during current transient is 3.338 volts. Actually, the real answer would be 3.3375, but here they have used a little rounding. So how this is found looks like a mystery, but it is actually not. So in this circuit, please look at the figure of the circuit. We have a logic gate, which is unknown and not so important for the circuit analysis. And we have two inductors, but we don't have any capacitors or any resistors, so we don't have any other component than inductors. This means that we can use this formula which we have given in the previous half of this video presentation. E, which represents the voltage of a inductor, a time varying voltage of an inductor. Please assume it is as V, as we use V much more than E for the voltage. So do not confuse it with energy or so. The total voltage is equal to L, the inductance value of that inductor, times di over dt. So di dt is the time varying current that passes through an inductor, and L is the inductance of that inductor. So if we multiply these values, we will get the voltage. Let's turn back to our question. Here we already know the combined inductance of these conductors, so we don't have to deal with two separate inductors. The question itself gives the combined inductance as 10 picohenries. Actually, the results suggest that the real numbers were 9.5 picohenries, but for the sake of simplicity, if you don't have a calculator with you, you can use 10 picohenries, but the result given here is calculated for 9.5 picohenries, and it should be exactly 3.3375. So anyway, what you should do here, multiply the current change, which is 175 amps per nanosecond. Please pay attention to this point. It's not per second, it's per nanosecond, which is 10 to the power of minus 9. And for the conductors, the inductance is picohenry, which is 10 to the minus 12. These will be important when calculating the multiplication. So again, what we should do here is to multiply this current value, the change of current, with the inductance, the combined inductance. So we have to multiply 9.5 picohenries, or you can also use 10 picohenries for simplicity, with 175 amps per nanosecond. So the multiplication becomes 9.5 times 10 to the minus 12 times 175 over 10 to the power of minus 9. So if you make this calculation, you will get the voltage that is recorded, that is obtained on the inductor elements combined. So in order to find the voltage that is obtained on the logic gate circuit element, we have to subtract the voltage of these combined inductors from the voltage of supply, which we also know is 5 volts. So the result of this multiplication is 1.6625 volts. And if we subtract 1.6625 from the 5 volts, which is the voltage of the power supply, we will get 3.3375 volts exactly. And this is the voltage that is obtained on this logic gate circuit. And it is also why we have it here as the result. Again, it looks like a mystery, but it is definitely not. It's very, very clear and straightforward. In these slides, there is a note for teachers, but I did not remove it because it says something very, very important, and I want to read it out loud for you to get benefit. Many of us will likely marvel at the IDT rate of 175 amps per nanosecond, which is a giant number. Really, it's a huge number, which equates to 175 billion amps per second if you multiply it with 10 to the 9. Not only is this figure realistic, though it is also low by some estimates. Some of the students may be very skeptical of this figure, not willing to believe that the computer power supply is capable of outputting 175 billion amps. Yeah, it sounds interesting, right? This last statement represents a very common error that students commit, and it is based on a fundamental misunderstanding of dI/dt. 175 billion amps per second is not the same thing as 175 billion amps. The latter is an absolute measure, while the former is a rate of change over time. It is a difference between saying 1,500 miles per hour and 1,500 miles. Just because a bullet travels at 1,500 miles per hour does not mean it will travel exactly 1,500 miles. And just because a power supply is incapable of outputting 100 is capable of, sorry, that could be a mistake, is capable of outputting 175 billion amps does not mean, so it appears to be correct. And just because a power supply is incapable of outputting 175 billion amps does not mean it cannot output a current that changes at a rate of 175 billion amps per second. So the amount of the change could be very small, but the speed of this change can be very, very high. And this example tells exactly the situation. So the voltage may travel from 0 to 3 volts, but this change could be very fast. This is the point. Let's move to another example. Inductors store energy in the form of a magnetic field. We may calculate the energy stored in an inductance by integrating the product of inductor voltage and inductor current. So P equals to I times V over time. So it's not inductor current, it's inductor current over time. Since we know that power is the rate at which work shown as W is done, and the amount of work done to an inductor taking it from zero current to some non-zero amount of current constitutes energy stored, which is shown as U. From these definitions, we get that P equals to dV dt, dW dt. Means that the change of work with respect to time, or derivative of work with respect to time, or time varying work change is equal to P. And from here, if we multiply both sides with dt, we will get dW equals to P dt. So you see the pattern here. Now what we should do is taking an integral to find W, and U equals to V equals to integral P dt if we take the integral of the previous statement. And the question asks here, find a way to substitute inductance L and current I into the integrand, so you may integrate to find an equation describing the amount of energy stored in an inductor for any given inductance and current values. The answer is U equals to 1 over 2 times L times I squared. So you wonder how we reached this point, and I will explain you how, although it's not written here. Let's read the note first. The integration required to obtain the answer is commonly found in calculus-based physics textbooks and is an easy power rule integration. In fact, it is one of the easiest and most essential integrations, and I will show you how we end up here. So, in the previous slide where we have this little information, we found out that u equals to integral of p dt. And we also know what P is. Here in this explanation part, we stated that P equals to I times V, current times voltage. So what we should do here is to substitute P with IV, and we will get U equals to integral IV dt. This is good, but we cannot proceed directly from here, so we should do one more thing. Now, in our hands, we have u equals to integral IV dt. And if you remember the previous example, one of the previous examples, we have defined the voltage, the time varying voltage of an inductor. And it is as shown here. Please think about it as V again, and V equals to L times di dt. So what we should do here is replacing V with L times di dt. So let's return back here. Now we will, here in this integral, we will have u equals to integral I times L times di dt times dt. So the two dt's, the one we already had here and the one we put below on a denominator from the substitutions, will neutralize themselves. So we won't have any more dt's but only di. So the formula, the equation becomes u equals to integral I times L times di. So it's I L di. And L is a constant number here because the integral will be I di, because we only have di. L is a constant number. It's only a factor, a multiplicative factor. It's not a variable. It does not change over time. So we can exclude it on one side. And we should take the integral of I di, and it is one of the most basic integrals. It will be 1 over 2 times I square. And if we do not forget and add the L here, we will eventually get u equals to 1 over 2 times L times I square. This is how we ended up here. Let's move towards another example here. Calculus is widely and falsely believed to be too complicated for the average person to understand. Yet anyone who has ever driven a car has an intuitive grasp of calculus' most basic concepts, differentiation and integration. These two complementary operations may be seen at work on the instrument panel of every automobile. And you see here an illustrative figure of the instrument panel of an automobile. On this one instrument, two measurements are given: speed in miles per hour or in kilometers per hour in the rest of the world other than US, and distance traveled in miles or in kilometers. Regardless of these units, the two variables of speed and distance are related to each other over time by the calculus operations of integration and differentiation. We have revisited this analogy a couple of times in our previous parts. Here we will be touching it again. And the question is, which operation goes which way? We know that speed is the rate of change of distance over time. This much is apparent simply by examining the units. Miles per hour indicates a rate of change over time. So if you cannot decide if a variable is somewhat constant or changing over time, then you can just analyze the unit. If there is time in the unit, like per second stuff, something, then it will probably change over time. Of these two variables, speed and distance, which is the derivative of the other and which is the integral of the other? Also determine what happens to the value of each one as the other maintains a constant or a non-zero value. The answer is speed is the derivative of distance and distance is the integral of speed. If the speed holds steady at some non-zero value, the distance will accumulate at a steady rate. So even if the speed is constant, the distance will increase, because if you think it logically, the reasoning behind this relation is very clear. If you are moving with a constant speed, it means that you are going from point A to point B. Means that your distance will be increasingly larger and larger. If the distance holds steady, then the speed indication will be zero, because if the distance is not changing, that means that you are not moving. The speed indication will be zero because the car is at rest. Okay, this question is not directly related to electrical engineering or very slightly involved in electrical engineering, but the speed and distance analogy is very good to understand derivatives and integrals, so we are not omitting it in our courses. Another one is coming. A forward-biased PN semiconductor junction does not possess a resistance in the same manner as a resistor or a length of wire. Any attempt at applying Ohm's law to a diode then is doomed from the start. So it's not the best practice to apply Ohm's law to diodes. This is not to say that we cannot assign a dynamic value of resistance to a PN junction, though. The fundamental definition of resistance comes from Ohm's law again, and it is expressed in a derivative form as such: R equals to dV di. This means that the resistance is the derivative of the applied voltage with respect to the current. The fundamental equation relating current and voltage together for a PN junction is Shockley's diode equation, which is I equals to IS times e to the QV over NKT minus 1. So if you are not familiar with PN junctions, semiconductors or diodes, do not worry. Just try to understand the changing nature of these relations and interrelated terms. At room temperature, which is approximately 25 degrees Celsius or 294 degrees Kelvin, the thermal voltage of a PN junction is about 25 millivolts. Substituting 1 for the non-ideality coefficient, we may simply get the diode equation as such: I equals to IS times e to the v over 0.025 minus 1, or I equals to IS times e to the 40v minus 1. So, differentiate this equation with respect to v so as to determine the I dv, and then reciprocate to find a mathematical definition for dynamic resistance, which is dV di of a PN junction. There is a hint. Saturation current IS is a very small constant for most diodes, and the final equation should express dynamic resistance in terms of thermal voltage, 25 millivolts, and diode current I. As I mentioned, this is a very advanced example, and even if you are not unfamiliar with these terms and these elements, you can try to understand the relation, or at least you can see how well calculus is used within the fields of electrical engineering. So I will not go dive deep in the details, but briefly give the answers. If you are already familiar with this stuff, then you can also do this calculation yourself. But actually, you don't have to know everything because it's just an integration and derivation question in its essence. So you can ignore their meanings to some degree and do the derivatives or integrals as we already have seen how we can integrate or take derivatives of these basic or well-known functions. R equals to approximately 25 millivolts over I. The result of this derivation is important in the analysis of certain transistor amplifiers where the dynamic resistance of the base emitter PN junction is significant to bias and gain approximations. And the solution steps are here because it's a neat application of differentiation and substitution to solve a real-world problem. It's not a made-up problem, it's a real-world problem. I equals to IS times e to the 4TV minus 1, and the IDV from here becomes IS times, because IS is a multiplicator factor, it's not a variable here. The IDV equals to IS times 40e to the 40V minus 0. So if you remember the derivative of the e function, e to the something function, the exponential function, you will remember that we do not change the original function but multiply it with the previous exponent. If you are struggling with these derivatives, you can check back our previous video or just type Google how to make derivative of exponential numbers, etc. There are tons of other resources, so you can just make use of any one of them. And in the next step, we will get di over dv, which is 40 times is times e to the 40v. Now we have to manipulate the original equation to obtain a definition for is times e to the 40v in terms of current. For the sake of substitution, current I is equal to is times e to the 40v minus 1, and I equals to is times e to the 40v minus is if we make the multiplication here. And if we move the last is on the other side, we will get I think actually I do not think, but I'm quite sure about that, there should be a plus sign because it is an addition. It must be I plus is equals to is times e to the 40v. Because we have moved the negative is to the other side, which will make it positive addition. Then there should be a plus sign, but it is not shown here for because of an error. But we can be sure about that. So I plus is equals to is times e to the 40v. And substituting this expression into the derivative, di over dv equals to 40 times I plus is. And reciprocating the to get voltage over current, the proper form for resistance, we will have dV on di equals to 0.025 over I plus Is. Here we have Is defined in this question. Okay, it's here. It's in the hints part. Saturation current Is is a very small constant for most diodes. So in many cases it can be ignored, but you are free to not ignoring it. Anyway, in practical applications, for most cases, you can ignore it, omit it, but not always. So here we can get rid of the saturation current term because it is negligibly small, and in this case we will get dV di approximately equals to 0.025 over I, and from this point we will get R, which is the time varying resistance, and this is why we write it with small letter R. It will be 25 millivolts over I, so it will change depending on the current. The constant of 25 millivolts is not set in stone by any means. Its value varies with temperature and is sometimes given as 25 millivolts or even 30 millivolts depending on the environmental conditions or the structure of the material. This example also concerns the speed and displacement analogy. It says that if an object moves in a straight line, such as an automobile traveling down a straight road, there are three common measurements we may apply to it. The position, usually shown with x, velocity, usually shown with v, and acceleration, shown with a. Position, of course, is nothing more than a measure of how far the object has traveled from its original starting location, and velocity is a measure of how fast its position is changing over time, whereas acceleration is a measure of how fast the velocity is changing over time. These three measurements are excellent illustrations of calculus in action. Whenever we speak of rates of change, we are really referring to what mathematicians call derivatives. Thus, when we say that velocity v is a measure of how fast the object's position x is changing over time, what we are really saying is that velocity is a time derivative of position. Symbolically, we would express this using the following notation: v equals to dx dt. Likewise, if acceleration a is a measure of how fast the object's velocity is changing over time, we could use the same notation and say that acceleration is a time derivative of velocity. So a equals to dv dt. Since it took two differentiations to get from position to acceleration, we could also say that acceleration is the second time derivative of a position. A equals to d to the 2 or d square x dt square. So, what has this got to do with electronics, you may ask? Quite a bit. Suppose we were to measure the velocity of an automobile using a tachogenerator sensor connected to one of the wheels. Oh, I see the electronics, right? The faster the wheel turns, the more DC voltage is output by the generator, so that voltage becomes a direct representation of velocity. Did you remember the potentiometer in one of the first examples? It's pretty similar. Now we send this voltage signal to the input of a differentiator circuit, which performs the time differentiation function on that signal. What would the output of this differentiator circuit then represent with respect to the automobile? Is it position or acceleration? And what practical use do you see for such a circuit? Now suppose we send the same tachogenerator voltage signal representing the automobile's velocity to the input of an integrator circuit this time, which performs the time integration function on that signal, which is the mathematical inverse of differentiation. as we have already discussed earlier. Just as multiplication is the mathematical inverse of division. What would the output of this integrator then represent with respect to the automobile? Is it position or acceleration? So again, what practical use do you see for such a circuit? The differentiator's output signal would be proportional to the automobile's acceleration, while the integrator's output signal would be proportional to the automobile's position. Because we have defined this analogy here and also here, position is nothing more than a measure of how far the object has traveled from its starting point, and velocity is a measure of how fast its position is changing over time. And if you look at here also, you will see that acceleration is the time derivative of velocity. Likewise, the velocity is the time derivative of position. So if we apply this information here, then we will get the answer. A, the acceleration, is proportional to the dv dt on output of differentiator. And so x is proportional to the integral. This is only one integral. It's broken down. Integral from 0 to t v dt, so the integral of the velocity. A follow-up question is coming. Draw the schematic diagrams for these two circuits, differentiator and integrator. This is also a very good one. We know that the output of a differentiator circuit is proportional to the time derivative of the input voltage. And here in this figure on the left side, you see a differentiator circuit which is implemented by an operational amplifier, a capacitor, and a resistor. Here Vout, the output voltage, as you see in this part, is proportional to the derivative of the input voltage with respect to time. But how do we turn this proportionality into an exact equality so that it accounts for the values of R, the resistance, and C, capacitance? Although the answer to this question is easy enough to simply look up in an electronics reference book or online, it would be great to actually derive the exact equation from your knowledge of electronic component behaviors. And here are a couple of hints. So this example is the differentiator version of the integrator circuit example that we have seen previously. The average current that is not time varying, shown as capital I, equals to capital V over capital R. So this notation is for time invariant variables, and it is usually representing an average value. And the time varying current, which is lowercase I, equals to C, the capacitance value, C times dV dt. So the time varying current is equal to the time varying voltage, the change of voltage with respect to time times the capacitance. And the answer is, for Vout, the output voltage, the answer is minus R. This is this resistor here, times C, times the time derivative of the input voltage. This answer, again, is not a mystery. It can be found using the given hints and the relation between the current and voltage within the given circuit diagram here. So time varying current is defined as C times dV dt, and the average current is defined as V over R. So what should we call V is here? First, V in, which is the input voltage, and lastly V out, the output voltage. So we have two different voltage values here. And we should also pay attention to find out what kind of substitution we should do. And here, if we apply these hints to our circuit, V out would be equal to I times R. But I here is also time varying, and this is why we should make a substitution over I. And for this capital I, we should use the time varying version of the current, and the equation should become V equals to R times lowercase I, which will be V equals to R times C times dV dt. So this will be almost exactly the answer what we have seen here. There is one little difference, and this answer is minus. So it's minus R times C times dV input dt. And the reason why we have a minus here is exactly the same reason why we have the minus in the integrator circuit. It is because of the phase shifts occurring because of this circuit structure. This is our final question. We will be finishing after this one, and it's a very fun question. You are part of a team building a rocket to carry research instruments into the high atmosphere. One of the variables needed by the onboard flight control computer is velocity, so it can throttle the engine power and achieve maximal fuel efficiency. The problem is, none of the electronic sensors on board the rocket has the ability to directly measure its velocity. What is available is an altimeter, which infers the rocket's altitude, its position away from ground, so it's the position with respect to ground, the distance from the ground, in other words. By measuring the ambient air pressure, and also an accelerometer exists which infers the acceleration, the rate of change of velocity, by measuring the inertial force exerted by a small mass. The lack of a speedometer for the rocket may have been an engineering design oversight, but it is still your responsibility as a development technician to figure out a workable solution to the dilemma. How do you propose we obtain the electronic velocity measurement the rocket's flight control computer needs? You can stop the video here and think about that maybe a few moments. One possible solution is to use an electronic integrator circuit, as we have seen previously, to derive a velocity measurement from the accelerometer's signal. However, of course, this is not the only possible solution. So, I would like to acknowledge the original source of the slides also. And what we wanted to do here is to inform you about the applications of some calculus concepts within the scope of electronics and electrical engineering. We have seen quite a few different examples which are all somehow interrelated, and I think that we have covered quite a few topics and provided a basic understanding of how can we utilize, how can we benefit from the calculus when we are doing our job. So that's all for today. Thank you very much for listening.